Hey, P-Stats. Second half of the Chapter 6 notes. You should be finishing this packet by the end of this video. So hopefully you got these notes done already from the previous video. And we're going to continue right here, just a small little part here. Shifting and scaling will not change features. This isn't that important, but just something to mention. Will not change features of a scatter plot. And we saw that shifting and scaling can change data distributions in the previous unit. We saw that with the dot plots. We mentioned how shifting can move them left or right, scaling, and we said all that stuff. So that doesn't affect our scatter plots in this case. All right, what we do want to talk about, and here's a huge part of this unit, is correlation. You've probably heard of this word. What correlation does is it describes the strength of a linear relationship. And you probably have heard this word before. So maybe think of something like this. There's a strong correlation between the number of minutes that you study and your performance on a test. All right, so that strong correlation, that's kind of that those two variables are related to each other. And with the word correlation, we have this actual stat unit, stat measurement, correlation coefficient. And this is also called R. And what this guy does is it tells us how strong that association is. How strong is that linear relationship? And it tells us on a spectrum from -1 to +1. I'll give you some examples here in between. So if I have a scatter plot that has a really strong and positive association, it would have an R value of 1. So it could look something like this. Maybe my scatter plot literally makes a straight line, straight linear relationship. That would have an R value of 1. Now, this isn't actually seen too often in stats because we know that most data in real life isn't always perfect. Let's do something maybe in between. Maybe if we had like an R value of 0.7. So maybe not as strong, but definitely there's still like a positive association here. And on the other end, what would an R value of -1 be? Well, this would also look similar to this guy, just in the negative direction. If I had similarly, actually let's go -0.5. So -0.5 compared to 0.7. This one is not as strong, so there should be more spread out data. But again, this one's still kind of going in the negative direction. Maybe something like that. So of these four that I just gave, the -1 and the +1 are the strongest. This is the strongest positive, and this one's the strongest negative. From there, then we have this 0.7, which is the second strongest, we'll say. And then this one is last. So what would something that has a correlation coefficient close to 0, what would this look like? Well, it'd be pretty much just a bunch of randomness. Doesn't look like there's really any association. So something like this. So this correlation coefficient actually tells you two things. It tells you if the association is positive or negative, and that you can just see from the number. And the second thing it tells you is how strong the association is. All right. Now, in the past, I have actually shown students how to calculate this correlation coefficient by hand, being that we don't really have time to do a bunch of fancy stuff this year. You can just cross out this third page, and we will not get to that this year. All right, so just jump to this last page. Oops, I'm not sure why there's two notes there. This last page down here, it says correlation, and we'll continue with that same thing. So again, that's that R value, the correlation coefficient, and it tells you two things. We said it tells you the direction of the association. So if you have a positive R value, we know that the general relationship is positive for the two variables. And then it also tells you how strong, or the strength, of the linear relationship. All right, now there are some conditions that have to be met for this. Conditions are something that in stats we are actually going to use a lot of. Now I'm going to introduce it right now, but as we move forward in the year, we can't just apply everything that we learn in this course to any data set. There has to be certain conditions that are met. So in this case, all the calculations that we're going to be doing for this unit, we need to have a condition that our data, the scatter plot, is it straight enough? Basically, does our association look linear? If the association looks linear, we can proceed with all the stat stuff that we'll be doing. If it doesn't, then we have to stop. Second thing is we want to make sure that we have quantitative variables. Really, that might be the first thing, but quantitative variables, you guys know this. These are things that we can count with units, not categorical variables. So we need two different quantitative variables. And the last one is this no outlier condition. And what outliers can do is they can significantly affect the models that we're going to produce later. All right. This last piece right here, correlation properties, this is still dealing with this correlation coefficient, this R value. And a lot of this will just be repeat, but it's good for you to see it again. So if it's a positive, we know that the association is positive, right? If your R value is negative, we know that the association is negative. Another thing, like I mentioned before, that this R value is always between -1 and +1. Where having a +1 is really strong and really positive, or having an R value of -1, it's also really strong, but it's negative. Something to mention with this correlation coefficient is that there's no units for this. It's just R equals whatever. And something interesting about R is that it actually stays the same if we switch our X and Y variable. So if I have something that looks like this, let's just say I wanted to switch my Y variable, whatever it was, to be the independent and have the X as the dependent. That may or may not change your graph. Even if it does, your R value stays the same if X and Y are switched. So R remains the same if X and Y are switched. Right. So causation and correlation, it is a huge, huge stats mistake to say that correlation equals causation. Just because two things are correlated does not mean that one causes the other. It does not mean that at all. And one example that I've seen in the past, you don't have to write this down, but I've always found this funny, and they've actually calculated the stats on this stuff. The global temperature, I don't know if you guys know, in general, from year to year, has been increasing significantly. So, like, I don't know, let's say we start at 1600, 1700, 1800, 1900. Let's say over here is 2000. So we know the temperature is increasing. One thing that has also happened as of late is that the number of pirates, like actual pirates, like the ones that go arr, those guys, they've been decreasing since the 1600s. So they actually calculated some stats on this stuff, and they found a pretty strong linear relationship that looked like this. So then this is where we have to be smart and know that just because there's a correlation doesn't mean that these two variables are impacting each other or are causing each other. Like, yes, there's a strong relationship here, but does that mean that the temperature has been killing off all the pirates? Like, no, that's not why it's happening. It's just a interesting correlation, but doesn't mean that they're actually related. So that's why you have to be very careful with stats. Just because things are correlated does not necessarily imply that they are caused by each other. And the reason that is there could be something called a lurking variable. It's kind of like a hidden variable that explains the changes in both x and y. So it could be a hidden variable or variables. So like in this case, maybe the number of pirates has died off because there's stricter police in the sea or international regulations in the sea. That could be a lurking variable, so that's why those numbers have decreased. And in terms of explaining why has the temperature increased, well, maybe we can look into something like global warming and seeing the amount of emissions that have been released by engines and stuff like that since 1600. So in that case, there'd be definitely a bunch of lurking variables. So we have to really examine why is it that there's a correlation here, not necessarily that these two are causing that. All right, guys, that's it for Chapter 6 notes. Go ahead and submit these. There are going to be a couple questions here coming up. So here's your first example. We have a association that appears to be negative, and what would an appropriate correlation coefficient, or R value, be for this scenario? Similarly, for this guy, what would an appropriate correlation coefficient be?